being caused by 5G mobile networks. And it's very easy to see how all of these sorts of things can start to put fear, uncertainty, and doubt into the population as to the safety of general technologies. And I think actually that with some of the stuff we've talked about today, the thing that might restrict it from going forward if we're not careful is the public acceptance of this type of thing.
Mm-hmm. Okay, great. So Xiaosheng, looks like we will have your answer in your talk. Yeah, yeah. So yeah, let's welcome to Xiaosheng to deliver the talk. So Kim, it's your time to be the guest hoster. Xiaosheng's talk will be the future all-in-one self-powered smart micro-nano system. Okay, Kim, please. Yeah.
Okay, thanks. Can you hear me? Okay, so
yeah,
very great to talk to you through this cool communication now, communication channel now. So first of all, I should really appreciate so much for again the Professor Alice and her all colleagues for all preparation and for inviting me to join this wonderful web seminar. And now, so yes, it's time to move to next talk. So actually, it's a great honor for me to introduce Professor Xiaosheng Zhang today and moderate his nice lecture from now. So today he will deliver the title of the talk is all-in-one self-powered smart micro nano systems, and which is self-powered, so-called effective ambient energy harvesting power source integrated micro nano systems and combined separated functional component, including a complete chain of sensing, proceeding, and responding of real Internet of Things. So which today is very fixed to this today's talk theme, I should say. So I very briefly introduced Dr. Xiaosheng Zhang. He's currently a professor at the University of Electronic Science and Technology of China, UESTC, right? And he received a PhD degree in microelectronics and solid-state electronics from Peking University in 2014 at Alice Lab, I think. And he joined the École Polytechnique Fédérale de Lausanne, EPFL Switzerland, as a research scientist, and also I heard he working as a research associate in University of Tokyo, actually at my lab since 2014 for 2 years. And he in 2017 he was awarded with a 100 talent professorship by the University of Electronic Science and Technology of China. So now Dr. Zhang is professor of that university, and his research field is a mechanical electronic system MEMS and cover the Micronano integrated fabrication as well as the application for smart system, where also he working now that kind of especially triboelectric nanogenerator power energy harvest. So please, so we will giving the mic to Professor Zhang now.
Okay. Yeah. Thank Professor Kim for the kind introduction. So just start sharing my screen. So can you see my screen now?
Yes.
Okay. Now I just show. Okay. So now. Okay. So thank Professor Kim for the very kind introduction. So I'm Xiaosheng Zhang from University of Electronic Science and Technology of China. So it's my great honor to join this wonderful the ICANX talks. It's my great honor to share the recent research progress in my lab. So actually in the field of micro-nano energy harvesting. But today my topic is all-in-one self-powered smart micro-nano systems. So in the way of the clean energy sources to power the Internet of Things. So recently the ambient energy harvesting mechanism based on the micro-nano technologies have attracted so much attention due to their the very unique features and properties. So they are named the micro-nano power source to efficiently harvest and convert the ambient energy to be the electricity. But actually, if we consider this kind of the micro-nano power source itself, we found that actually we can use them not only as the power source, but we can also use them as the sensor and as well as the actuator. So in the way of this point, we wish to combine them together to realize this all-in-one self-powered smart micro-nano systems. So I will introduce this topic from the following 5 parts. The first is research background and motivation, and then I move forward to the to introduce the work about the high performance nanogenerators. And then I've introduced how we can use this nanogenerator to realize cell-powered sensor and actuators. And finally, I will show you that the feasibility to realize the cell-powered smart the micro-nano systems. And then I will give some the summary and the perspective. So as you know that the research field in my lab is about the micro-nano electromechanical system. So what is the nano electromechanical system mean? Of course, this is also as known as the MEMS or NEMS. So let's say this is the typical, for a typical MEMS or NEMS, the system, so it contains three functional components. The first is micro-nano sensors. So based on this kind of sensors, we can detect the changes in the environment, and then we can convert these changes to be electrical signals. And these electrical signals will be transferred to the data processing units, and then their control signal will be generated to reflect what happens. And then this control signal will be sent to the ending of the micro-nano actuator to tell that, okay, so actually we need to respond to this change in the environment. So this is the three functional components to construct a typical the MEMS or NEMS the systems. So if you look inside these three functional components, we found that all these functional parts need power to be driven, right? And also, since this the micro-nano systems, actually the feature size of this kind of system is quite small. Normally in the scale level of the micro scale or even nano scale. So it also brings the challenges to the power source. So we know that all these functional parts need power, and also due to the feature size of this the MEMS or NEMS system is quite small, so it brings some new challenge to the power source. So this new power source can be summarized as we need a high performance the power source, and we need the power source to be the sustainable. And normally we wish this power source can be, for example, if you have the sustainable power source, it means that you don't need to recharge this the devices frequently. I mean that the devices can work autonomously, and also we wish to integrate these all functional parts together to form the smart, the cell-powered micro-nano systems. So in the width of this point, we consider that actually there's very attractive future vision if we combine these power source components and a functional component like the sensing component and actuating components together, so we can realize the cell-powered autonomous and smart micro-nano systems. So for example, if you, as you can see in these slides, so just to give me 1 second to get the laser point here. Okay, so you can see here, we just drawn the prototype that's what does it look like for this cell-powered the smart micro nano systems. So they contain the several parts. The first part, of course, it should be that we have to integrate this micro nano energy harvesting devices with the micro nano sensing components together, and then we can also integrate the proceeding and responding component together, and sometimes we need the human machine interface like this the smart display. So we integrate these the whole the components together and to form this the cell-powered the micro nano systems. So this power source means that we need to convert the energy from the human body itself, and as well as the energy in the environment. So the question is how we can do this. So we know now that will be a promising method or approaches to realize the energy harvesting that is can be used to supply the working of the micro nano system, right? So we know that is the energy harvesting from our living environment. But the question is how to harvest and convert the environmental energy, such as the sunshine, the thermal dissipation, and body motion, and airflow, and even the ocean wave, to be the electricity. So actually, the scientists and researchers have developed several technologies, so such as the photovoltaic effect, and the thermoelectric effect, and the electromagnetic effect. Actually, based on this, the electromagnetic effect. So you can realize that the wireless power transmission, as is the talk introduced by the professor Eric and Paul. and as well as the piezoelectric effect and the triboelectric effect. So due to the time limitation, it's not allowed me to give more details about each of them, but I still wish to guide you to see that actually each technology, they suffer some disadvantages, and of course they also own some advantages. For example, for the photovoltaic effect, you can always get the direct current output, and also actually this technology is the very mature the industrial fabrication technology. So it means that the cost of this technology is quite low. So we can use it to generate the cost of the power, electricity. But if you look inside the working principle of this, the working this energy harvesting mechanism, you will find that it only can work on the light. So it means that if you use the devices in the dark, so it actually doesn't work. So that is the problem for this technology. Of course, each of these technologies, these suffer some disadvantages or drawbacks. But today I'd like to emphasize one of the very quite new technology that is named the triboelectric Nongenerator. So what is the triboelectric Nongenerator? Let's see. We know that triboelectrification effect actually is very common, ancient phenomena. Actually, is already discovered by people. That is, history can go back to 3,000 years ago. So if you just check up the clothes in the very dry air, you will hear that is some noise, and also you have the feeling about the discharging. So these charges is generated by this triboelectrification effect actually. So when two different materials contact in a friction, you will get the charges at interface. So this is the triboelectrification effect. But actually, initially, people consider this triboelectrification effect as a negative effect. For example, if you want to assemble some chips to the PCB board, you have to wear the gloves, or you have to discharge by contacting the fingers to some metals to discharge the charges to protect the chip. Otherwise, the high voltage of this the triboelectrification we just damage the chip. But in 2012, actually, the scientists in Georgia Tech, led by Professor Zhongli Wang, invented one very interesting devices named the triboelectric Nongenerator. So how it works? Let's say there's the figures I placed here to show that is how we can generate the electricities based on this the very emerging mechanism. So actually, we just placed the two metals, as you can see here, two metals on the backside of the two different materials. So when we applied the compressive force to the devices, and then to make these two materials contact and the separation, so there will be generated the charge at interface. And one material is very easy to lose electrons and show the positive potential, and for the other, it's very easy to capture electrons and show the negative potential. So when they are separating, so there will be internal electrostatic potential will be the field, electrostatic field will be generated between them. And then due to the electrostatic induction, so there will be charges transferred from the backside electrodes, one of the backside electrodes to the other. And then we can get the power that is current actually. So in summary, for this kind of devices, the working principle is based on the combination of triboelectrification effect, in which we can generate the charges. And then the second is electrostatic induction. It means that the charges can be transferred from one of the electrodes to the other. And then if you connect them together by a load, and then you can accumulate the charges, and then you can get the power. So it's very simple. The structure is very simple, but it's very useful actually. So I see at the bottom left corner, you can see this is the output signal waveforms. So there's two pulses in a single circle. So one is a positive pulse and one is negative pulse. So it's just corresponding to the separating and approaching process. So that is what we can get from this the triboelectric Nongenerator. Okay, so after about since the first device is proposed in 2012, so you can see that it's almost 80 years. So after 80 years development, the device is already proven to be a robust power source. And here we can see that the power density of this kind of devices have already achieved to about 100 the million watt per square centimeter. And the highest efficiency can achieve to 85%. So it's quite attractive. I mean, for some low power consumption devices or systems, so it means that this technology can provide the sufficient the power for this kind of devices or the systems. And for different the configurations have been developed to realize the devices. So just to summarize here. So the first one is contact separation mode, and these two layers just move in the vertical direction. And the second type is a relative sliding mode. It means that these two materials have the relative the motions in the horizontal direction. And then the third one is the single electrode mode. It means that you can use the human skin or some other the materials as the separating layer. But for the device itself, it's only contain one electrode. And the final one is the freestanding mode. That is, you place the two electrodes at the bottom, and then we have another the charger, the layer just to move atop this the electrodes, and then we can collect the periodical the transfer the chargers. So this is a 4 different working principle of the devices. And so we can summarize it. For this kind of technology, it possesses several attractive advantages. For example, the first one is a clean energy source. It means that there's no any pollution to the environment, right? It's not there's no some gas or some other the harmful the materials just released to the air. And also actually the device is sustainable. It means that if you continuously to provide the external stimuli to the devices. For example, you just use the finger to press the devices continuously, and then you can continuously to get the power. So in this way, we said the device actually is sustainable. And also, if you say that the power density and efficiency, and of course, as well as the voltage and current, we see that compared with some other the Micronano harvesting technology, like the piezoelectric generator. So this kind of the triple-electric Nongenerator have the better output performance actually. And also the structure is quite simple. Simple means that actually the cost of the device is quite low, and it's very easy to be integrated with other the functional components. And also there's no materials limitation. But here it's worthly mentioning that actually it doesn't mean that so for example, for the piezoelectric energy harvesting devices, you have to use the materials that possess that is the piezoelectric the properties, right? But for the triple electric Nongenerator, so it exists in all 2 different materials. Even some water flush in forward and backwards in the polymers, it can also generate its chargers. So in the viewpoint of this, so we said there's no materials limitation. But as just like the other technology, this the triple electric Nongenerator is also experiencing some drawbacks, like the output performance need to be enhanced further to meet the power demands of the practical applications. And also the fabrication process of the devices should be simplified. And also we need to figure out or find out, explore some the environment-friendly materials to minimize the side effect of the materials itself that is construct the devices to the environment. And also to functionalization. It means that we wish to integrate more functional component to the systems to realize the Micronano systems. So we can summarize that there's 2 very the common or the important essential tendencies for the development of triple electric Nongenerator. The first is the performance enhancement, and the second is multi-functions integration. So our work is just in these two directions. So I've introduced the more details about our work. So the first part is about the high performance nanogenerators. As we said before, so in order to meet the power demand of the practical applications, so we need to strengthen the output performance of the devices. So how to do it? So let's see. So if you look inside the working principle of the triple electric Nongenerator, we found that it contains two different mechanisms. The first is the triple electrification effect. The second is electrostatic induction. So triple electrification effect is very essential. It means that the charges is generated by this effect, right? So it means that the effective friction is the key point of the electrification. So to induce the surface charges. When we move into this field, scientists that have developed several techniques to enhance the output performance of the device. They fabricate the devices with the microstructures, either with the microstructures or with the nanostructures, because you can enlarge the surface roughness of devices, right? So in this way, we can enlarge the friction area, and then you can enlarge the surface charges. Okay, so the simple idea is, can we combine them together? So we can combine, if we can combine the microstructures with the nanostructures together, and then to form the micro-nano hierarchical structures, and that means that we can further enlarge the friction area, and then maybe we can strengthen or enhance the output performance of the devices. So based on this simple idea, we developed a fabrication technology by using the silicon-based the deep reactive IHM process to realize the single step, the micro-nano hierarchical structures. And then, but the silicon, we know that is very useful materials to serving as the basic stone to construct the whole semiconductor industry. But silicon materials itself is very fragile, so it's not suitable to construct the variable or the flexible the energy harvesting devices. So how we can figure out the solution? So here we combine this silicon-based the micro-nano hierarchical fabrication technology with the softer materials, the pattern replication process together to form the softer materials, the micro-nano fabrication technology. And then we can transfer the patterns from the silicon-based mode to the softer materials surface. In this way, we fabricated the PDMS and the Parylene and some other, as well as the silicon. So it means that we can fabricate the micro-nano hierarchical structures atop the softer materials surface, and then we can use this kind of softer materials to construct the high-performance nanogenerator. And then the surface of these devices can be maximally enlarged. So I show you that the devices we fabricated here is look like the sandwich. So we call it a sandwich-shaped the triple electric Nongenerator. As you can see, this is the layer in the pink color. So this atop the surface, it was fabricated with the micro-nano hierarchical structures. So for the microstructures, there's the pyramid arrays, and then atop the pyramid arrays, there's the nano porous atop the surface. So this is the first triple electric Nongenerator that's employed the micro-nano dual-scale structures, and then we can greatly enhance output performance of the triple electric Nongenerator. So if you go back to the year that we published the work on nanogenerators, actually that is the highest record for this kind of the triple electric Nongenerator. So you can see here that is what it can achieve to 465 volt, and the current density achieved to the 13.4 the microampere per square centimeter, and also the power densities go up to almost is over the 15 microwatt per square centimeter. So that is the work. So that is the first enhancement. The technology we developed is based on the surface, the roughness enhancement based on the Micronano fabrication technology. And then the second method for the power, the output performance enhancement we developed is the surface plasma treatment. So if you look inside for this triplet Nongenerator, we have found that actually the charges generated is always on the top of the surface at interface of the two materials, right? So then we consider maybe we can treat the surface to change the chemical or the because for the surface roughness, actually you change the physical the physical property of the surface, and then we consider maybe we can also use some technology to change the chemical properties of the surface. In this way, we maybe also can enhance the output performance of devices. So based on this idea, we developed one technology that is still through the deep reactive IHM process by using the inductively the coupled plasma equipment, is ICP equipment. So we enhanced the passivation step and then to deposit the fluorocarbon materials atop the surface. So as you can see at the left corner image here. So we deposited this fluorocarbon materials. It's very thin layer, just the tens or several the nanometer the thickness atop the surface, and then you can change the chemical property of the surface completely. So we also use the theoretical, the first principle calculations to calculate the vertical, the ionization energy of the model complexes. One is the PDMS, that is the conventional materials to construct this triplet Nongenerator, and the second one is the fluorocarbon that is deposited by using the DRE process. So we found that compared with the traditional materials, the PDMS, the fluorocarbon, the vertical ionization energy of the fluorocarbon, it can go up to about is over 12 eV, and for the PDMS it's only about 9 eV. So it means that compared with the traditional material, the PDMS, the fluorocarbon thin layer, possess a very strong ability to capture electrons. So when you have fixed another materials serving as the true electrical pair, and then you treat the PDMS surface by using this plasma treatment, and then you coating the very thin, the fluorocarbon thin layer atop the surface. So it means that it's very, you just make the devices, make the materials of the PDMS is harder to lose electrons, or in other words, it's very easy for this fluorocarbon materials to capture electrons, and then we can enhance the output performance of the devices. It means that you can enlarge the surface, the charges generated by the triple electrification effect. So the surface plasma treatment is firstly proven to be the powerful to enhance the output performance of the devices. So that is the second, the enhancement method we developed. And the third one is the hybrid mechanism. If you still remember that we talk about that actually the scientists researchers have developed several technologies to realize this, the micronano energy harvesting. It's also named the ambient energy harvesting technology. For example, the photovoltaic effect and the piezoelectric effect. There's 5 main technologies. So each of them experience some advantages, but it also suffers some disadvantages. It means that there's the perfect technology. So we just think that why not? If we can combine the 2 or more energy harvesting mechanisms together, it means that you can combine the advantages of these 2 or more the mechanism together. So maybe we can enhance the electrical output performance further, right? So, for example, there's a devices we invented firstly. So this is the R-shaped devices. You can see this is the layer in yellow color. This is the materials of PVDF one of the polymeric materials, the piezoelectric materials. So when you apply an external force to these R-shaped devices, so the deformation will be generated. So this deformation will generate the piezoelectric potential at the two ends of these the metals. And also when the piezoelectric the layer we just move forward downwards to the bottom PDMS materials with the Micronano hierarchical structures, there will have the triple electrification effect. And then in this way, we combine this piezoelectric mechanism with the triple electric mechanism together. So in other words, just in a single circle, working circle. So when you apply a single external force, actually you generate two electric outputs. So in this way, we can enhance the output performance of the devices further. So that is, we said, is why we wish to combine the two or more the energy harvesting mechanism together, which is also named the hybrid mechanism. So this is one of this work. And also later, we integrate the devices with the keyboard. And then we consider that for the wearable devices, actually we wish to realize that all fibers, the hybrid nanogenerator. So it is also based on the hybrid mechanism by the combination of the triple electrification effect and the piezoelectric effect. So here you can see there's two conductive fabrics. So we fabricate, we prepare this the nano-wise the network of the silk fibers. And this one is the PVDF nano-wise network that is fabricated by using the electrospinning process that is fabricated on top this the fabric, the conductive fabrics. So then we can fabricate the devices that is in the form of the all fibers. We also investigate interaction between the piezoelectric effect and the triple electric effect. It means that actually it's not always they have some positive interaction. Sometimes they also have the negative interactions. For example, we know that for the piezoelectric materials, they also have different polarization directions. So if you change these directions, maybe the generated charges will not keep in the same direction of the triple electric generators. So then we said is these two, the energy harvesting mechanism has the very well, it's very bad, the upside state. And in other, in contrast, if they keep in the same direction to generate the charges to enhance that, so we said these devices will be in the coordinate state. It means that they can enhance themselves. So in this way, so we can enhance the output performance of the devices. That is, we said, is by using the hybrid mechanism to realize or form the hybrid nanogenerators. So that is the third energy harvesting enhancement technology for the triple electric nanogenerator. So this is the three technology we have to carry on in our lab. And then, so I would like to move forward to the next part about the cell-powered sensor and actuators. We know that we always talk about this technology, the Micronano energy harvesting technology, ambient energy harvesting technology. So actually, if you consider inside this kind of the technology, we found that we always employ some mechanism or working principle, like we said, the photovoltaic and piezoelectricity or the triple electricity, to convert the external impulse to be the electrical signals, right? It means that you convert the vibration, strength, or strain, or bending, or rotation, deformation. You convert this kind of the environment changes to the electricity. So it means that this electrical signal also contains the information of the environment changes. So from the external input, we can realize energy harvesting. that we said is nanogenerator. But if you consider it in the opposite direction, we found that actually we can use electrical signals to detect the environment changes. So in this way, we can use these nanogenerators as the sensor. And also, even you consider this nanogenerator, of course, you can use them as the power source. But actually, the electrical signals can be used directly as electrical stimuli, and then we can realize some cell-powered actuators. It means that you can use the devices not only as a power source, but also as the sensor and actuators. So that is, we said, is why we can realize this cell-powered sensor and actuators. It means that just to respond that to the question we discussed previously, how we can replace the battery. So for the power storage at this stage, it's very hard to say that we can replace the battery. But in some specific case, like if you want to use the electric signals generated by the nanogenerator directly to stimulate some actuators, or some you consider itself as the sensors. So in this way, actually, we don't need the battery, right? So that is maybe one of the possible the solution to realize the batteryless the devices. Okay, so let's say how we can realize the cell-powered sensors. So I have several samples to show you that. The first one is cell-powered humidity monitoring sensor based on the tubular nanogenerator. So we know that the water molecules in the air will just bring the effect to the devices, because it will cause or induce the discharges of the surface at the interface of the two materials due to the charges will be disappeared. So we know that. So when we measured the output voltage of the devices under different relative humidities, here you can see. We can use the devices of the tubular generator to quantitatively to detect what is the relative humidity in the environment. So in this way, we can say that the devices can be used to monitor the humidity in the environment. So in other words, based on the effect of the humidity on the output performance of the tubular nanogenerator, so we can realize this cell-powered humidity monitoring sensor. And the second sample is that we can place the devices. We can place the devices at the human the joints, like the anchor or some other different the joints. So the developed the wearable tubular nanogenerator has been successfully demonstrated to recognize the motion of the human joints, such as the bending or the twisting of the waist joint. And you can see, so in different gestures, so you can get the different the output electrical signals. So we can detect the angles of the waist, and also we can tell the difference of the bending or the twisting of the waist joint. So that is, we said, is how we can realize the cell-powered sensors by the devices. So in principle, there's two different types of cell-powered sensors can be realized by using this nanogenerator. One is using the electrical signals generated by the device itself to reflect the changes in the environment, right? And as well as we, in the meantime, so we can realize the cell-powered sensors based on the effect of the environment factors on the output performance of the devices. So just as I showed it here, like the cell-powered humidity sensor, and as well as the sensors for the detection of the human joints. Okay, So this is about cell-powered sensors. As we said, it actually we also can realize the cell-powered actuators. So how to do it? We know that for the micro-nano energy harvesters, normally we need to treat the signals generated by the devices to get the DC electric signals, and then these DC electric signals can be used to supply the working of the portable devices or the wearable devices and some other the traditional conventional devices, right? But in this way, you always have to the power management circuit, and sometimes you have to use the energy storage devices like the capacitor or the battery even. But if you consider that we use these electrical signals generated by the device directly, so for example, if you look inside the device, we found that there you always get the pulse. That is a form of the which is a form of the electrical signals. And then maybe we can use the pulse directly as the electrical stimuli signals. In this way, we don't need the power management circuit, and we don't need the battery or some other energy storage devices. So in the view of this point, we can realize the cell-powered actuators. So here I just show you several samples we have demonstrated. So the first one is that we use the triple electric Nongenerator driven an implantable micro needle electrode array to stimulate the schematic nerve of the frog leg. So you can see here, here is implantable micro needle electrode array that is fabricated atop the surface of the PI substrate, and the micro needle is the micro needle are made of the gold. So we just insert this the implantable micro needle or electrode inside the muscle of the frog leg, and to close to the zone of the sciatic the nerve. And then when you use the finger to press, this is the triple electric Nongenerator. When you use the finger to press the devices, so there will be generate the electrical signals, and these electrical signals will just delivered to this the micro needle electrode array, and then there will be electrostatic uniform the field generated to cover the zone of this nerve, and then this nerve will be stimulated, and then the frog will just move forward and downwards as your finger to press the devices. So this is when the samples to say that it's cell-powered the devices that we the cell-powered actuators we fabricated by the integration of the microneedle electrode array with the triple electric Nongenerator. And the second example is about the manipulation of water droplet. We know that in the micro nanoscale level, actually the water manipulation is not so easy. It's very hard actually, because you have to apply the high pressure to push the droplet move in the desirable direction, or the design direction. So here we just we know that if you look inside the electrical signals of the triple electric Nongenerator, we found that the voltage is quite high actually. So this the high voltage means that you can generate the high electrostatic the field. So we just connect this triple electric Nongenerator directly with the droplet through the conductive needle, and then we can control the motion direction of the droplet by fix the conductive needle position with the droplet. So for example, just here we define the 4 points, that is the positive X and negative X, and positive Y and negative Y. So in different direction, we can control the motion based on the relative position of the conductive needle and the droplets, and we can control the motion of the droplet. In this way, we can realize the controllable the water droplet manipulation. For example, if you place the conductive needle at the point of the positive Y, so when you press the triplet Nongenerator by using the finger, so the pulse generated will deliver to the conductive needles, and then there will be the high the static electrostatic field generated at interface of the droplet and the substrate, and then the droplet will move in the direction that is in the direction of the positive y-axis. So if you place the conducting needle at the point of the positive x, and then the droplet will just move in the direction of the positive x. So in this way, we realize the controllable the manipulation of the liquid droplet by using the triplet Nongenerator. So without any external circuits or some other the complex the microfluidic the channels, so we can control the motion direction of the droplet. So I have two videos to show with to share with you to see how we can. Okay, so I just plan it again. You can see here. So we place these two the droplets. You can see here that is the micro needle, and then we just insert this micro needle on the right side of the droplet. So when you press the triplet Nongenerator, and then the output electric signals will apply to the interface of the droplet and the substrate, and then there will generate the symmetric electrostatic force. So the droplet will just will be forced to move in the direction here. So let's say the video. So that is how it works of the devices. And this is the two droplets we placed here, and then there's two the conductive needles. One is on placed in on the right side, and one is placed on the left side. So when you apply when you press the device by using the finger, so there will be electrostatic force which generated between them. So these two droplets will move in the direction to each other. So there will be so these two droplets will be mixed together. So this is the second samples, the self-powered actuators we developed. And then the final the powered actuators is about the MEMS cantilever. We know that the MEMS cantilever or the MEMS switch actually is very, very powerful and useful to realize the micro nano systems, especially in the field of the radio frequency, the MEMS, in radio frequency MEMS or NEMS. So here we just simply connect this the electrode of the. So here is the micro cantilever, or you can call it a MEMS switch. And here is the model of the triboelectric on the Nongenerator. So we connect the electrodes of the top. We connected the top electrode of this T and G with the bottom electrode of the cantilever, and we connected the bottom electrode of the triboelectric Nongenerator with the top with the cantilever of the MEMS switch. So when you apply the force to the triboelectric Nongenerator, so it will be generate very large electrical the powers. And this powers, since we connect these electrodes together, so the electrode signals generated by the TNG will transfer the charges to the surface of the cantilever, and then there will establish then one of the very large the electrostatic field will generated will be established between the cantilever and the bottom electrode. And also we calculate how to control the switch on and switch off state of the cantilever. So actually this equation is very typical. So we just figure out that is how we can control the gap of how we can design the gap of the triple generator, and as well as the gap of the cantilever. So then we know that when we apply the force to the triple nanogenerator, so the cantilever will in on state or the off state. So this is the first demonstration and the systematic analysis of the driven mechanical the micro devices by using this kind of the triplet nanogenerator. And here is the video I wish to share with you that to see. So this is the device of the triplet nanogenerator, and then this is the cantilever, the MEMS cantilever of the MEMS switch that is connected with this triplet nanogenerator. So when you use the finger to press the devices, and here is the microscope to see that is what happens between the cantilever and the bottom electrode. So let's see what will happen. Okay, just give me 1 second to move this. Okay, so we see that when you use the finger to press the devices, so there we one of the electrical signals will be generated and applying to the cantilever and the bottom electrode. So you can see the controlled motion of the cantilever. So this is, we said, is the cell-powered actuators. It's very useful actually. So we can control the on and off switching, the state switching of the MEMS cantilever by designing the gap of the nanogenerator. So we use the integration of the triplet nanogenerator and the micro cantilever the systems later. I will show you that how we can realize the cell-powered smart system. Okay, so let's move forward to the final parts actually. That is the cell-powered smart, the Micronano system. That is the part I wish to emphasize. We said that we talk about the triplet nanogenerator. We use this device as the power source. And we also said is actually, if you consider the relationship between the external inputs and the electrical, the output signals, so you can use the devices also to detect the changes in environment factors. It means that you can use the device as the sensors. And also we can use the electrical output signals directly to stimulate the actuators, so we can realize cell-powered actuators. So now we have the power source, right? We have the cell-powered sensors, and we also have the cell-powered actuators. So can we combine them together? Can we combine these different multiple functional components together with the power source, and then we can realize cell-powered, the cell-powered smart micro nano system? The answer is yes. That is also the main research field in my lab. So we still to see. I still wish to bring the prototype we proposed back to you. So you can see here. So the idea is we wish to harvest the energy from human body itself, and also to convert the energy in the environment to power the micro nano system itself, and then to construct the micro nano system, we wish to combine the power and the multi-function together, and then we can realize the cell-powered, the smart, the micro nano systems. So that is the idea. So how to do it? So let's say several attempts. So first is, so before we start the cell-powered microsystem, the description. So let's say one of the very important materials that is widely used to construct this kind of the triplet nanogenerator in my lab. So that is the silk fiber. So silk is very common materials, especially for Chinese people. We know a lot about the one belt, one road, right? So that is tell about the story of the silk actually. So here is to show you that this is the bovine marine cocoons that we used to extract the silk fibers, and then we dissolve these silk fibers to get the silk fiber solution. So this is solution after the extraction and dialysis and the micro filtration. So we get the pure silk fiber solution. So that is a water-based solution. It means that there's no any some organic solvent inside. It's just water and silk fiber. And this silk fiber is come from the 100% natural bobbin mooring cocoons. It means that this silk fiber is also 100% natural. And then the water, and then the solution is water-based solution. So it means that this material is very, very safe. It's biocompatible and completely safe materials. There's no any side effect to the environment. That is, we said, is the green materials actually. So this images show that how we can prepare this the biodegradable silk fiber film from the completely natural mooring cocoons. And why we use these materials? There's three reasons. There's three reasons actually. The first one is outstanding transparency. You can see here during the whole variable range, this material is completely transparent. It means that you can use these materials to cover some devices and without changing the optical properties of devices. And also, this materials possess a remarkable water solubility. So here we put inside these materials. Okay, so you see these materials with in the blue the color. That is, we add some blue dye inside. Otherwise, it's invisible. Okay, so we put it inside the DI water, and within 13 seconds, so this film just disappeared completely because due to its remarkable water solubility. But here, it worth mentioning that this water solubility actually can be justified by using alcohol annealing and water annealing and adding some chemicals. Okay, so there's the third reason we employ these materials to construct the triple-action Nongenerator. We can see here, this table shows that materials, the capability of materials to lose or capture electrons. So here on the left side, if you just look the direction from the bottom to the top, you can see the materials is easier to lose electrons and show positive potential. And for the right column, so the materials from the top to the bottom is very easy to capture electrons and show the negative potential. So it means that you can see here the silk is occupied the top tier position and possess outstanding ability of losing electrons easily. So that is the reason why we employ these materials to construct the triple-action Nongenerator. Okay, so here let's say the devices. Actually, I talked it a little bit in the former slides. So this is all fiber, the hybrid Nongenerator. So I just wish to emphasize that here. So you can see, compared with the traditional material, the silk fiber significantly enhanced the output performance of the devices by 8 times. It means that compared with the traditional or the conventional materials, the emergent materials possess outstanding the charges accumulation or generation capability actually. So how we can realize these micro systems? So I'd like to show you that this is the schematic wheel of this whole self-powered microsystem. So here is the triple-action Nongenerator, so the devices to generate the power. And here is the cantilever. If you still remember that we talked about this, the system that is in the previous slides. So, and then this cantilever will serve as the switch. And then this switch will connect with the wireless modules. So, for example, this is the all fibers devices we fabricated. So when you wear these devices and you swing and slide and streak, so normally, and then the device will just serve as a power source and generates generate the electricity without any the other functions. Because when you use the device, when you wear the devices and to do some normal the gestures, you get the power. But the power, the signal generated is not large enough to actuate the cantilever. It means that the voltage generated by the Nongenerator is not large enough to change the working state of the cantilever. So it's just to keep in the off state. It's only in the case that you streak your arm, quickly and sharply to the desk to stimulate, that is, people falling down. So then the generated electrical signal is large enough to change the state of the cantilever. So then this cantilever will just will send a trigger signals to the wireless modulants, and then the signal will be transferred to the remote monitors like the cell phone or some other portable devices, and then to tell people that is urgent. Some people, the people that is where the device is falling down. So this is, we said is cell-powered microsystem, and with the smart, the functionality. So that is to realize the remote emergency core, the microsystem for the real-time falling down the detection. So it contains the dual the functions. One is for the energy harvesting, and one is for the falling down the detection. So that is one of the prototype that is how we can realize this cell-powered microsystem. So let's see the one video. Okay, so we just use we wear the devices here at the bottom of the arm, and then we just strike the desk sharply and to stimulate that is some people the falling down. So you can see, okay. And then there's the signal we generated and sent by the cantilever we just in the on state, and then the wireless the signals we transfer to the remote monitors. Here is the cell phone, and then to tell people someone they're falling down. And in other case, actually, they just the normal working as a normal energy harvesting the devices. This is the first the cell-powered micro systems. Okay, so I have the second cell-powered microsystem. So we wish to integrate it more functional, the sensing, the more multiple the sensing functions together with the power, the generating. So here it's still based on the silk fiber materials, and this is a preparation how we can get this solution. And here, this is the PDMS, and we use the screen printing process to print the interdigital the graphite electrodes atop this PDMS substrate. And then we dispense this silk fiber solution atop this graphite electrode to cover it and to form the silk fiber film. And then the devices keep the excellent flexibility. Okay, so let's see how we can we can integrate the different sensing the functions and with the power generating the function together. So here are the devices, and we connect these the two pads with the LC meter, and this is the photograph and SEM images of the devices, and you can see this is the graphite the electrodes prepared by the screen printing. So this is a flexible printed sensor, and which can be used to distinguish the water existing states. So we know that the water molecules exist in the air actually in two states. One is liquid water molecules. One is the gaseous water molecules. So for some humidity sensors, they just detect both of them. So for them, I mean that they have the reaction with both of these liquid state and gaseous state water molecules. They can't tell the difference of them, but due to the selective absorption property, the capability of the silk fiber. So here, these devices can selectively reactive with the liquid water molecules, and there's no any reactions with the gases water molecules. So it's very interesting to realize this the water existing state sensors. Here is some more data to show you the effect of the interdigital electrodes gap and silk fiber film thickness. And finally, here we realize the passive sensors. What does mean the passive sensors? So here you can see that is the capacitance based the passive sensing. So it means that we use the LCR meter, we apply voltage to the devices, and then we detect what is how is the capability the capacitance changes. So in this way, it means the passive sensing. It means that you have to apply actual the power to the device, and then you can get some changes to see what happens of the humidity and whatever. So here, this is the passive sensing we said is realized that based on the devices we fabricated, and then we use it to distinguish the breathing of the human. This is normal and deep and fast. Okay, so this is the passive sensing. And also, we use the devices serving as a single triple electric non-generator. It means that we can generate the power by using the devices, so the same devices. So with the hand pressing, so here you can see that during one cycle, it can realize more than 100 nanocoulomb charges transferred. This is very large, actually. So the power, the total power generated by the devices can go up to 4 the milliwatt. So it's very large, actually. And then, as we said, it's passive sensing. Actually, the devices also can serve as active sensing. So compare with the passive sensing. Passive sensing means that you have to apply the power to the devices, and then you get you can know that to detect the changes. But for the active sensing, it means that, for example, we use the device, we use the electric signals generated by the device itself, and then we can know that when you move the hand, you can detect the angles change and the gesture changes from the bending or the twisting. So this is active sensing. It means that you don't need to apply any the actual power source. You just use the power, you just use the electrical signal generated by itself. The changes of this kind of the electrical signals you can detect or sense or sensing the changes of the stimuli. So that is, we said, is active sensing. So for the second samples of self-powered microsystem, we combine the passive sensing with the active sensing together, and as well as the power source to realize this is self-powered smart microsystems. Okay, so I still have the third, the self-powered micro systems share with you. Okay, so for this work, we integrate the radio frequency, the identification, the torque together with some nanogenerators. So we know that for the traditional the RFID, the radio frequency identification torque, so they use the 2 coins coupling to transfer the power, right? To deliver the power, and then you can read the data that is stored inside the radio, the RFID torque. And here, but the working distance of these devices is quite short, actually. It's normally just about 10 centimeter. So and also there's only can realize the single the direction, the communication. So that is the the limitation of this technology. So here we wish to realize the active on the RFID torque microsystem. So we developed firstly the hybrid nanogenerator. You can see here by the combination of the triple electrification effect and also the electromagnetic effect. And also we developed a new the power management the modules, and then so we realize this the active RFID torque. So compared with the passive, so you can see here this is the passive RFID torque. So the working distance is quite short, and also you can only have the one direction communication. For this self-powered active RFID, so we can convert the biomechanical energy that is generated by the working running. So here we just plant the device, integrate the device with the shoes, and then we can realize the self-powered devices. You can realize the long working distance. You can see here the working distance enlarged by the 300 and more than 300 times. And also we can realize the dual communications. It means that this active RFID tag can send or transmit the data to the receiver, and also the receiver can read the data stored inside this the radio the RFID card. So that is, we said, is this device realize the dual communications. Okay, I will just show you 2 videos. That is, okay, so there's the students where the devices we fabricated. So we just convert the energy of the working. So it means that without any battery or some other the energy storage. Of course, here we use the capacitor to store the energy. But without any the batteries, and then the devices can work independently or autonomously. And also we developed the app the integrated with the cell phone to tell you that is how the distance between the people, that is where the device is, and so it can realize the real-time the detection of the distance. So it's very interesting work, I think. So in this work, we show that is actually we can use this technology to harvest the energy from human body itself, and then to powering the microsystem itself. It means that you don't need any power. You don't need to, for example, to recharge the battery frequently. So the power just comes from your body itself. So in this way, we realize the cell-powered microsystem is very useful. And then this is the 4 samples that is we realize that is we wish to show people that is actually there's a lot of the feasibilities we can realize the cell-powered microsystem, and not only based on the tube electric non-generation, but also some other the devices. So here we show you that the variable, the double chain thermoelectric generators. So these devices also serve as the multi-functional sensors, which further improves the integration of the variable electronics. I don't think that I have enough time to go more details, but I just wish to guide you to see that actually here is we still use the screen printing process to fabricate the double chain the thermoelectric generators, and then when we get the functional patterns atop the substrate, and then we cover it with the silk fiber film. So, and then finally we get the devices like this, okay? And also we prepare the P-type the ink, and this is the N-type ink, and then we can print the double chain devices atop the flexible substrate. And this is the working principle of the devices, and also the output and the output performance measurement of this the thermoelectric devices changing with the different temperature difference, and also the mechanical reliability evaluation. It shows very good. Okay, so here it means that the device can generate the power, right? And each chain. So here we have the 2 chain, right? So for each of the chain, it can generate the thermoelectric output signals. And since these 2 chains has the configuration, it look like the interdigital. So we cover these interdigital patterns with the silk fiber. So then we can censor the change of the humidity, and as well as some to tell the difference of the existing state of the water molecules, as we explained before. Okay, so and also we also investigate the effects of different temperatures on the function of the water molecule sensing in the air. And finally, I would like to show that actually the powering capability of the fabricated device is quite good. So here we show you that just the students wear the devices on the arm, and then several minutes later we can successfully the powering the commercial the calculators. So it's very useful. So in this work, we said a cell-powered microsystem means that the devices itself can be used to harvest the thermal dissipation, and also due to the functional the patterns configuration design. It means that the double chain the configuration, so we can realize the temperature sensing, and as well as the water molecules existing in the air sensing. So that is we said is cell-powered smart microsystem. Okay, so final the attempts. I just go through quickly. So here, if you still remember that we talk about the tube electric non-generator, we said you always get during when the cycle of the working cycle of the devices, you always get the positive and the negative pulse, right? So this positive and negative pulse actually is not so good, because if you want to use the device as a power source to power some electronics, you have to convert it to the direct current, right? It means that the negative part you can't use it. You have to convert it to the positive part, and even you have to use some the power management to get the flight the electric signals. So the first component you have to use, that is the full wave rectification circuit. It means that you have to convert the positive part, the negative part to the positive part. So this full wave rectification circuit actually is just to increase the power consumption, and also it will make the integration of this Micronano energy harvesting devices is complicated with some other functional devices. So if we can change it, I mean that for all these existing for the working mode, the mode of the devices, all of them just generate this positive and negative powers during one working cycles. So if we can develop the one devices that can generate, that is unidirectional the current output, it will be very useful. It means that we never need any the full wave rectification circuit, and then we can simplify the configuration of the devices and make it very easier to be integrated with some other functional devices, right? So that is one of the working direction in my lab to we can simplify the structure of the devices, and then to make it more easy to realize the cell-powered microsystem. So due to the time limitation, I will not go further some technical the contents of the work, just to show you that. So the key point of this work is we developed an innovative design of the periodical literal cantilevers. And with the help of the combination of the specific patterns conductive networks, and then the cantilevers placed on the combo bars, so the motion of the charge is controlled in the sole direction to form a unidirectional current flow. Okay, so this is a device, and that is the electric output measurement. And so finally, you can see here, we use the devices to successfully to power the commercial, the temperature, the sensor, and also the commercial calculator, and some also studies of the electrical signal. So okay, so the final is about the prospects. So we wish to realize the cell-powered, the micro, nano, the systems. It means that we want to integrate the sensing, proceeding, actuating together, and as well as the power source. So the devices or the systems, the Micronano system can get the powers by itself, and then so it can work autonomously, and it can for a long or term period. And there's a selective publication if you wish. So we have worked some, in my lab, we have worked in the direction, 4 directions. That is the sensing, the prospection, and the radio frequency maps devices, and then harvesting devices, and finally the system integration. So I would like to thank Professor Xiaosheng Zhang. Actually, Professor Zhang is also my PhD supervisor, and Professor Jürgen Brugger. That is, we work together when I stay in EPFL, and also Professor Bongjun Kim. I work as the research associate in the Professor Kim's lab for almost 2 years, and also my colleagues in UESTC, Professor Wen Huang, and Professor Chen Tu, and Dr. Chen Xingong, and also my colleagues and researchers and students at UESTC. And this work is also financially supported by the NSFC and some other fundings. And thank you so much.
Okay, so once again, I appreciate so much for very nice talk and very impressive. Many various wide range of tank devices, power generator, also integrated with some of the sensor in all-in-one system. It's quite interesting and promising. So thanks a lot. So now we have to time to some question and comment about the audience. So first question is, maybe you can see here. So yeah. Thanks for the nice talk. The Micronano composite structure greatly improves the output performance of tank, yeah, you said. And what is the robustness of this Micronano structure during work? So after working for a period of time, is there a significant some attenuation or something? So that is the first question.
Okay. Yeah. Thank you so much. Actually, this is a very good question. because people always, when we see the working principle of the device, we found that we have to apply some external force or some other stimulation to make it have the friction. So friction is very good because you can generate the charges and interface. But frictions also mean that you maybe bring some damage to the surface. I guess this is the reason that is why people they have this concern about how about the long term the working capability or the output performance of the devices. That is, we said is what is the robustness of this Micronano structures. Okay, so actually I didn't plan it here, but just if you still remember, can you still see my screen now? No.
No.
Okay.
No.
So okay, it's fine. I will just explain. Okay. So if you still remember that when I say that is first step to get this Micronano hierarchical structure, we fabricate these patterns by using the deep reactive IHM process. We realize the structure by using this DRE process on silicon substrate. And then due to silicon is fragile material, so we transfer this patterns by using a replication process from silicon mold to the PDMS substrate. And then since the material is flexible and soft, so we also have carried out the experiment to see how about the long-term reliability or the stability of the devices, and we found it's very good. So we have done that the continuous cycle about 13,000, more than 13,000. So it still keep very good the output performance actually. Of course, we also have done that the SEM observation to see maybe some change. That is yes. The answer is yes. So the geometry or the morphology of the surface, that is said is micro nanostructures, it has been changed. But since the key issue for the device's performance is about the roughness, so even the profile of the micro nanostructure changed a little bit, but actually the output performance of devices still keep very stable. So that is my answer. And so just a shortly summary that the profile of the micro nanostructures will be changed a little bit, but output performance of the devices still keep very stable.
Okay, thanks. So, well, and then the second question we will go. There is Professor Zhang, amazing talk. I'm wondering for using the output signal of tank as an active sensor. So how to calibrate? So this kind of data for the using for the sensor. So how about the reliability as well? That is second question. Well, so you need a calibration, for the signal.
Yeah, actually, it's very good question. I found that the audience is many experts actually. Okay, so the calibration of the active sensor fabricated by the Nongenerator actually is very how to say they bring a very essential challenge actually. So it's not so easy to do that. So currently, people just still working in the stage of demonstrate the feasibility of to realize this kind of the active sensor. So it means that we try to show people that we can realize this different kind of the cell-powered active sensor, and but the calibration is not so much work working in this direction. I think it's a very good topic that is in the future we can walk in that direction. So that is my answer about the calibration.
Okay, and the reliability of some maybe power generation also depends on the environmental as well, which can be used for the sensor. Reliability also very important.
Okay, so since I already answered the reliability of the devices serving as a power source. Okay, so if you consider the devices serving as the active sensor, so actually, as I explained before, the active sensor means that we use the generated electrical signals directly to reflect the change of the how to say, the external inputs. So in this way, we said it's active sensor. So since the output performance of devices serving as the power source is very stable, of course, sometimes there's some decline addition we have observed after a very long term the working, but in principle, it's still very stable. So in viewpoint of this, so we can say that serving as active sensor, so this kind of the devices is still very reliable. So for example, if you still remember that the devices, the first samples I show you about the self-powered humidity sensor, we use the silk fiber. So the devices, you see that when the relative humidity increased, so the curve will just decline gradually, right? So actually, when you join the devices in the normal environment means that just the temperature is about 25 centigrade, and just the normal relative the humidity. So the devices will just dry, and then the output performance of the device just recover completely to the original state.
Okay.
So that is mean that the device actually is very reliable, right?
So you mean, so even the humidity affected like a material of the silk, but it is still in conventional normal ambient environment is still reliability is very high, you mean, right?
Yes.
Okay.
So it mean,
okay.
So it means that it can recover completely to the original state after joining.
Okay, thanks. So maybe there's another question, third question. There is also thanks for the wonderful talk. And the third question is, how can tank power smart electronics there will be universal power management circuit in the future? It's also funny question. So about this power management and circuit inside the circuit, yeah.
Yeah. Okay, so I think it contains two small questions. The first is, how can TNG the power smart electronics? Okay, so I think it depends on the practical applications demos. For example, what kind of the smart electronics you wish to power. So here, since I also talk about the smart cell-powered, the smart Micronano system. So smart, it means that we, in my own opinion, we think that is for smart, it means that you can detect some changes in the environment, like the humidity change and the temperature change, and also some other change. For example, if you still remember the first demonstration I show you about the cell-powered microsystem, so we fabricated the devices to detect the falling down. So that is a cell-powered falling down the microsystem. It means that when people falling down, so we generate the huge pulse, and this huge pulse will switch the state of the cantilever, and then we will send a signal to the remote, the portable devices like the cell phone, to tell people that someone or some person they just fall down. So that is the smart. It means that you can detect, but this detect is just detected by the device itself. There's no any human reaction. It means that it's not by using the eye or some other human to detect. So that is, I think, is smart. And also for the okay.
Oh, really? Okay, so
sorry.
that is maybe one good question. So the other one is also congratulations. So this audience is curious about if this tank device can be used to power the implantable devices, which is more important for long-term implant. So for example, in the body inside. So that kind of thing can be used or not. That is question.
Okay, so thank you so much.
About your opinion?
Yeah, thank you so much for the good question. So I just very quickly to give my answer. So yes, the answer is yes. Actually, due to the time limitation, I didn't put all my work inside here. So actually, we have one work that is we harvest the energy from the heart beating, and then we put the devices inside inside some the animals to do the animal experiment, like the dog and also the pig. And we found that actually we can harvest and generate sufficient power can be used to power the implanters or implantable devices. But
so answer is a yes. So does it depend on the packaging, on the material?
Yeah, the materials. Yes.
Okay.
Yes.
Okay, so maybe we'll go to next fifth audience case result. A lot of cases already. Yeah. So I'm in Qingjing from UEST, so same university, I guess you're. And as to the self-powered microsystem that can detect the movement of falling down, it is related to the soft and hard contact, and how to adjust and control it. That is question.
Yeah, this is very good question actually. As we said, of course, it depends on the soft or the hard contact. So we have established the two modulars. One is for the TNG, and one is for the suspended cantilever, and then we combine them together. So we have the equations to calculate how we can design the devices. But of course, the devices mean that it also depends on how you apply the impact to the TNG. So the answer is yes. And how to advise and control is you can just use the equation to calculate the gap of the devices, and then you know that how large the impact you need to control, and then you can stimulate the different age and a different kind of the people when they're falling down, how large the electrical impulse it can generate it.
Okay, thanks a lot. So I guess it's a final question, or maybe there are a lot of, so then Alice can select it, a good one. Sixth question is from also University of Electronic Science and Technology of China, Tao Feng, maybe the first professor. This is a great report. I have a question about the durability of the device. So we all know the friction layer of a trivial electric nanogenerator is vulnerable to damage, so which is more prominent for the fiber-based nanogenerator. So you want to ask if there is a possible solution to achieve excellent durability, so the long-term durability. So what are your opinions?
Yeah. Okay. So yes, there's a lot of the challenges we need to figure out how to we can overcome this the drawbacks. For example, the washable is also the key issues that is for these wearable devices. When you talk about the wearable, people always want to ask you, if you wash the clothes, you wash the devices, what happens for the output from the devices? My answer is we have to try to figure this problem from in the following aspects, like the materials and the configuration. For example, the package or some other the technology that we can use. For example, some people try to use the surface plasma treatment to treat the surface and to make it more robust. Okay. I hope I answered this.
Yeah, thanks. Oh no.
Thank you.
Congratulations.
Thank you.
Thank you.
Thank you.
Congratulations.
That's the certification for you. So Xiaosheng, technology to connect the world and the universe, try to build up a lot of new things. As it's a smart system, I'm really counting on that. That's for you.
Thank you so much. Thank you.
Thanks a lot.
Okay, cool. Yeah, this is the end of today. So this is also the end of this seasons for the third season of technical report. As you know that we're writing technical report for each speaker. So after their talk, so will be given out on Monday. So this was the third series of this technical report. So be sure to download that by scan this code. It's very interesting technical report, also very helpful. And next next week we will have a big day because it's lighting the world to celebrate the 60th anniversary of laser. So this will be special sponsored by Light. Yeah, the journal. Yeah, this journal, we all know that is the top journal in the light field. Yeah, so it's a very good journal and very successful stories. So yeah, we will have all these speakers in next week. And also save the date for MAPS. As MAPS conference next January will be online, so I will be the chair, one of the chairs. Yeah, so be sure to save the date to support our big conference. And that's our ICANX talks. So yeah, we still have many speakers, will get on the stage. So I'm looking forward to see you next week. Yeah, connect word on the universe, get on board our ICANX talks. Okay, see you next Friday. Okay, yeah. Okay, thank you very much.
Bye-bye.
Thank you so much.
Thanks.
Ah.